What's the tallest mountain on Earth? Chances are 99% of you immediately thought of Mount Everest. After all, it's the single point on Earth that stands highest above sea level, and it's really not close, with it being about almost 1,000 feet or 300 meters further from sea level than its next closest competitor. Well, what if I told you that height above sea level isn't the only way to measure a mountain, and in these other metrics, Mount Everest isn't even close to the highest mountain? This is how there's more than one tallest mountain on Earth. Now, before we get into that, I'd appreciate you to like the video, subscribe to the channel, and hit the notification bell to stay tuned for future content. Okay, so how exactly can you measure a mountain? And by extension, which are the highest mountains on Earth under each metric? Well, there are three main ways of measuring a mountain: height above sea level, distance between a mountain's base and its summit, and its raw distance from Earth's center. Let's start with the metric most people are familiar with, which is height above sea level. This metric makes sense since sea level is largely universal across the entire planet, with only very minor local fluctuations between different regions. As a result, this provides a convenient benchmark for determining how tall a mountain is. As stated before, this is the metric Mount Everest holds the gold medal in, coming in at a whopping 29,035 feet or 8,848 meters above sea level, which is more than twice as tall as any mountain in the Rocky Mountains or European Alps. This extreme height is because Mount Everest is still a relatively young mountain, having only formed a few tens of millions of years ago when the Indian tectonic plate collided with the broader Asian plate. Because India is still being subducted under Asia, the Himalayas are actually still growing at the rate of about an inch or 2.5 centimeters per year. Older mountains like the Rockies and Alps have been more worn down by erosion, with the tectonic forces that created them having long since subsided. However, despite being an easily accessible benchmark, height above sea level has a couple significant drawbacks. Perhaps the biggest one is that it fails to gauge how truly tall a mountain is, since a small mountain could easily sit on top of an extremely high alpine plateau and still be the highest point above sea level thanks to the added height from the plateau below. Another issue is that climate change, either warming or cooling, can dramatically affect the elevation of sea level due to how much ice has frozen at the poles, which can superficially change the height of mountains like Everest without actually changing the mountains themselves. So, despite being convenient, height above sea level definitely isn't a perfect indicator for how big a mountain truly is. So, what else can we try? Well, another way of measuring mountains is how far they are from Earth's center. This would in theory work out if Earth was an absolutely perfect sphere, which would allow the size of mountains to be measured without relying on the variability that sea level can bring. So, what's the tallest mountain in this category? Well, it's actually not Mount Everest, but rather an unassuming volcano in Ecuador known as Mount Chimborazo, which climbs to a comparatively modest 20,548 feet or 6,263 meters above sea level. So, why is this the case? Well, the truth is, Earth actually isn't a perfect sphere, but rather what's known as a geoid, which is essentially a sphere that is slightly flattened around the top and slightly wider in the middle. In the case of Earth, this works out so that the radius at the equator is about 13 miles or 21 kilometers bigger than it is at the poles. Since Chimborazo is located just half a degree south of the equator, while Mount Everest is about 30 degrees north of it, it works out so that Chimborazo is about 7,000 feet or 2,100 meters further from Earth's center than Everest, thanks to the added distance provided from the equatorial bulge. This also has the side effect that Chimborazo has a very slightly smaller gravitational force from Earth than most other places, due to the extreme distance from Earth's center, as well as the increased centrifugal force from Earth's rotation of the equator. In addition to the lack of a perfect sphere, there are a few more issues that prevent the distance from Earth's center metric from catching on. For instance, it is plagued by the same problem as the above sea level metric in that a tiny mountain on top of a high plateau could in theory claim the title of furthest from Earth's center despite being a smaller mountain, which is kind of what's happening with Chimborazo and the equatorial bulge. Another major problem is that the units involved are not exactly all that friendly, as the distance from Earth's center is represented in thousands of miles/kilometers instead of feet or meters. Due to how relatively smooth Earth is at this scale, with the difference between the highest mountain and deepest trench being just 11 miles or 18 kilometers, the actual variation in distance between two landmarks is really tiny. And finally, it is really, really clunky to say, Right now, I am exactly 3,965 miles and 2,482 feet from the center of the Earth when expressing your elevation. So suffice to say, nobody is going to talk about elevation in those terms anytime soon. This brings me to the final major way to measure a mountain, and that's the raw base to summit height of the mountain itself. With this metric, you are looking at height based on that mountain and that mountain alone, without needing to worry about variable sea levels, the extreme units needed to express distance from Earth's core, or any external landforms surrounding the mountain that may skew its height when basing it off of other metrics. So with all that in mind, what's the highest mountain in the base to summit category? Well, once again, it's not Everest and it's not Chimborazo either. Instead, the title goes to Mauna Kea on Hawaii's Big Island. On the surface, it's not the highest mountain above sea level, only reaching about 13,796 feet or 4,205 meters above sea level. In addition, this low height combined with its latitude at about 20 degrees north means it is in no contention to be the furthest from Earth's center. However, the true scale of the mountain becomes apparent when we dive beneath the waves. Mauna Kea's slopes extend for an incredible 18,000 feet downward before it reaches the Pacific Ocean floor, which, when combined with the above sea level portion, combines to a staggering base to summit height of 30,610 feet or 9,330 meters, a number which is bigger than Mount Everest height above sea level. One can only imagine the sheer insanity of looking up at Mauna Kea from the bottom of a drained Pacific Ocean and seeing a mountain that stretches seemingly infinitely upward. So, knowing that base to summit is the best way to express the actual height of a mountain, why don't we see it everywhere? Well, base to summit is the great way to measure how big an individual mountain is, but it's too localized to really be useful outside of that. Simply put, if we use base to summit as our benchmark for elevation, two places at the same elevation compared to sea level could have radically different positions relative to their respective mountains, and that's not even accounting for the vast swaths of Earth's surface that don't have mountains at all. Furthermore, while sea level can and does fluctuate, it does so on such a small level that it doesn't really affect the general picture when it comes to elevation, which includes stuff like the higher up you go, the cooler it gets. However, there are some things that base to summit is incredibly useful for. For one, it's one of the main ways that ski areas are measured, as a ski area with a significant spread between its base and its summit is likely to be bigger and have more variety than a ski area with a more modest height spread. Additionally, base to summit is used when there is no benchmark like sea level to compare elevation against, which is the case for pretty much any mountain outside of Earth. For example, Olympus Mons on Mars measures a staggering 72,000 feet or 21.9 kilometers from base to summit, which is about 2.5 times taller than any mountain on Earth. So, moral of the story is, base to summit is useful for individual mountains. Elevation compared to sea level is useful if you want to describe how physically high you are, and distance from Earth's center is all but useless. No offense, Ecuador. And that's all I have to say about how mountains are measured. As always, I'd appreciate you like the video, subscribe to the channel, and hit the notification bell to stay tuned for future content. Thanks and have a great day.